Okay, students, Dr. Billman here. I'm currently in my office. You can see it's becoming to look a little bit more increasing like a radio host studio. Like I've got my microphone here, I got a bunch of laptops, I got my tablet, but I'm getting tired of not doing chemistry, so let's go do a demo. Okay, so I'm in the lab room. It's been a while since I've been in here, but I think that this room would be perfect for this type of demo since there is like great lighting, not too much ambient sound, no one's really on campus. You might hear a little bit of an echo, that could be a little bit of a problem, but if you were there so many months ago during the, Marvelous Metals ACS webinar kind of technique, we did a little bit of a demo beforehand. It happened very quickly, a little bit of reaction kinetics there, but we're going to be doing the same demo to demonstrate reaction mechanisms, but with a little bit of a twist. Okay, so what we have here is a solution of potassium permanganate. Inside of it also is sodium hydroxide. Again, I apologize if there's a little bit of an echo in this room. It's not like I can control the sound dampening in here, but what we have right now is a stable solution. The solution will not decompose. It will remain this beautiful purple color, purplish pinkish color, until we add a source of sugar. Now, sugar is a really great reducing agent. Potassium permanganate inside is a really great oxidizing agent, and so when these two things mix, they're going to perform a redox reaction. So the source of sugar that we used before when running this demo, and if you didn't see it before, don't worry, you're going to be seeing it now, hopefully in a better form. The source of sugar before was just straight up sugar, like glucose sugar, in powder form, same kind that you would be able to buy at the grocery store. What I'm going to be using this time is a sucker. This sucker is connected to a batter, stirrer, and so when I push this button here, we get the sucker to spin. So this is hopefully going to be giving us a really nice stir inside of the solution. Let's see what happens. Right, famous last words. Let's see what happens. Okay, so this is Dr. Billman in post, because I realized as I started stirring the solution, the cake batter that the electronic device that I was using to stir with the sucker was just making a horrendous sound. You could barely hear my voice even as I switched to this. So I am now editing this in post. Now, as the solution is being stirred by the sucker, what we can see, as has been happening so far, is that the solution has gone from this bright pink color to this very dark purple. And as I pull the sucker out, what you can see is that it's like this very dark, almost it's got like a blue or green sheen to it. All right, so let's discuss as to why, what's actually happening after we just kind of get the visuals of the reaction. So I continue stirring, and the froth you can see now is shifting very clearly to a forest green sort of color, away from that kind of dark purple blend. Give it one last little stir. So what I've been doing is mixing in the sugar from the sucker as the stir stick has been stirring with the sucker. Now as I pull it out, you can see as I'm going to show it to the camera a little bit more, that sucker has been eaten away for sure. As I set it down behind the Erlenmeyer flask, we can see the solution now is lightening up. The green color is sort of fading away, and we are being left with this kind of muddy brown color. And the muddy brown color also now is continuing to lighten into this bright sort of orangish amber color. So the question is, what is happening here, and how does this demonstrate reaction mechanisms? Well, we started the reaction with a manganate ion, which is characteristically a purple color. This was combined with sugar, causing a redox reaction. Now, the first sort of reversible step that is occurring, this is a very fast step, is that the manganate ion, which is characteristically that purple color, is reduced with 2 electrons to manganate with a 3- charge and is blue. This is what caused the very dark color in solution. It's a very deep, deep brown. However, the manganese with a 3- charge is very unstable, so it's going to cause it to reoxidize back into that manganate with a -1 charge and is characteristically purple. So we have this kind of competition going on between that forward and reverse reaction. The manganate, though, with that 1- charge, is also able just to be reduced by 1 electron via sugar in this redox reaction, which is turning into a manganate with a 2- charge, which is known to be green in color. And so this reaction, as the manganate is being reduced into this green color, the green color then is able to be further reduced, also via a forward non-reversible redox reaction. And this reaction can take place without stirring, without agitation, the manganate being combined with water and 2 electrons into manganese oxide, which is characteristically an amber color. Now, how this reaction demonstrates reaction mechanisms is that we can write one big overall reaction for what we just saw. The manganate, which is purple, being combined with sugar and 3 electrons to create the manganese oxide, which is amber in color. However, as we saw, this reaction took place over a number of steps, the manganate turning into the dark blue solution, which slowly faded into green, which slowly faded into amber. And so we have to acknowledge the fact that these reactions do not take place in one big step, that the purple did not just turn into amber right away, that there were multiple steps that occurred in the reaction stepwise. And this is a demonstration, therefore, of reaction mechanisms.